And I think we're going to move into our luncheon presentation at this point. So I'll ask Randy to come up and introduce our speaker.
Thank you, Tony. It's my pleasure to introduce our luncheon keynote speaker, Professor Robin Craig. I'm having a bit of deja vu at the moment because I actually believe met Robin for the first time in 2006 when I was, or 2007, when I was a professor at Florida Coastal School of Law in Jacksonville, Florida, and invited her to be a keynote speaker on a topic related to climate change and public health, and it was a very provocative and engaging talk, and the reality of climate change law and policy is so much has changed and yet so much has remained the same, and I think there's a piece of that here that we've been aware of climate change and public health intersections for a while now, and Robin was at the forefront of those developments 13 years ago, and she continues to be. So it's really exciting to have someone who's been thinking about these interesting and scary connections between climate change and public health, and particularly now in the context here in the New Jersey coast, which is my first year here. It's an issue that Robin brings a lot of expertise to. Her self-proclaimed expertise is all things water, which is daunting enough in scope that would include ocean and coastal law, and she's an internationally known scholar on ocean and coastal law and water law, and she's seen those issues from both coasts of the U.S., having been based at Florida State University College of Law, where she and I overlapped for 1 year when I was a visitor there, and now she's based at the University of Utah College of Law, and seeing things from a different perspective, but also a lot of the same themes. And climate change, on top of all of those areas of expertise, she's been a leader on climate change law and scholarship on climate change law and policy. So with all that breadth of expertise, what I enjoy most about Robin is that she's just a very engaging and down-to-earth speaker in person, and a wonderful colleague to have on these issues. Kind of keeps things relevant, but also accessible and entertaining all at the same time. So without further ado, happy to introduce Robin Craig.
Well, thank you, Randy, and thank you for inviting me to be here. What Randy neglected to mention about that first invitation was he said, yeah, you're going to be a keynote, come and listen to presentations for a day and a half and then summarize them all on the fly at the end of the conference. So that was a lot of fun. But as Randy said, I circled back to public health and environmental law, public health and climate change on a regular basis, and hopefully this works. There's some reasons for that. I think reframing a lot of issues as public health when you can have some real legal and policy and public relations advantages. So there are many uncertainties surrounding climate change impacts on the sea, especially sea level rise is the big one. So how do we deal with uncertainty? The time scales are pretty long, longer than are typically involved in planning efforts. Getting 50-year horizons is kind of a new thing in planning efforts. And a public health focus can take some of these uncertainties and make them politically salient, address real human needs, and help to identify some practical and hopefully no regrets efforts that can benefit adaptation efforts more generally. So I've done this in a couple of different focuses recently. One I looked at after Hurricane Harvey was just how toxic a lot of our coasts are, and I'm cognizant that I'm in New Jersey, probably don't have to explain that one very much. But Harvey in Houston really demonstrated the toxic load that our coasts have, and posed a lot of real risk to human health from the air pollution, from the water pollution, as a result of all the infrastructure that got damaged during Harvey. This talk, I am turning back to something I started earlier in my career with disease burdens. It actually didn't occur to me until this morning that this may not be an entirely appropriate lunch subject, but here we are anyway. All right, so I'm going to give some representative examples from 3 impacts of climate change that might be most relevant to changing disease burdens. First, ocean water temperatures are rising. We all know that. Second, the seas are rising, so sea level rise related to ocean warming, but also has some different impacts of its own. And then finally, the weirdest one, probably the science fictional element of this talk, is what might be happening with the melting ice. All right, so starting off with ocean warming. Anthropogenic global warming has warmed the world about 1 degree Fahrenheit, a little bit more. And the ocean is the largest gatherer of that warming. It covers 70% of the Earth's surface. It can absorb a lot of heat content without actually changing temperature radically. And 90% of the warming that has occurred in the last 50 years has occurred in the ocean. So bringing along with it some interesting developments in science. As is true often with climate change, one of the things we're finding is it's happening faster than we thought. So ocean warming is one of those. It's happening, according to some recent studies published in Science, about 40% faster than the IPCC projected just in 2014. So, like I said, with many things accelerating. Sea surface temperatures have obviously gone up the most, but ocean warming has been detected down to at least 3,000 meters at this point. So, what loves hot ocean water? Vibrios, okay? The genus Vibrio has about 100 species. There's about a dozen of those that cause human disease. And they love warm water. So, Vibrio volnificus, and this is going to be the grossest picture I do, but Vibrio volnificus is one of the Vibrio species. It's present in marine environments. It likes coastal waters, it likes estuaries, and it likes brackish waters. It's a human pathogen. You get higher concentrations of it in warmer weather. So traditionally that was May to October. And during storms. It's got 2 paths of infection for human beings. You can get vibriosis from Vibrio volnificus by eating raw or undercooked shellfish. Or, this is the gross one, if you go swimming in Vibrio-infected waters with an open wound, you can get some pretty horrific diseases, skin infections. It's called a flesh-eating bacteria. It's not the true flesh-eating bacteria, but it does get that label. If you're infected through an open wound, about 1 in 7 people die who do that, and about half if it gets into your bloodstream. So that's the more deadly of the infectious route. Another Vibrio that's worth noting is Vibrio parahemolyticus, sorry. And this is a more standard intestinal disease causer. There we go. All right, so again, gets into raw or undercooked shellfish, or it can get into drinking water. You can get infected by this Vibrio through drinking water. It likes warm water, especially prevalent in the United States and the Gulf of Mexico, but that's not it. So those are 2 of them. And then, of course, the biggest Vibrio of all is Vibrio cholerae, the cholera-causing bacteria, which also likes warm sea waters. But I'll get to that in a second. All right, so what's been happening with Vibrios is they've been spreading. They've been spreading northward and southward. As early as 1996, Israel noticed that it was experiencing systemic Vibrio vulnificus infections among fish market workers. They were getting it from the fish, which correlated pretty intensely to high temperatures in Israel. The Vibrio vulnificus season in the Gulf of Mexico, I said, used to be May to October. It's now April to November, so that's been expanding as well. Vibrio infections have been traditionally relatively uncommon in Europe, but the infections are increasing, and this is kind of charting on both sides of the Atlantic, the different Vibrios that were sampled over time. The outbreaks in Europe are increasing, especially following warm weather, and the 2016 conclusion from the study in PNAS was that a warming trend in sea surface temperatures is strongly associated with the spread of Vibrio. So going up the Atlantic coast of the United States, spreading throughout Europe. All right, and so Vibrio infections have been increasing in the United States as well, and you can see that they've gotten all the way up here, New York, Massachusetts, experiencing some incredible infection rates for those two states in 2013, which is correlated to higher temperatures, I'll get to in a second. All right, there's been a geographical expansion of the parahemolyticus version of Vibrio in outbreaks. They've occurred as far south as Peru and as far north as Alaska, which is not the traditional range for Vibrio. They are closely associated with climate anomalies like El Nino, which bring large masses of abnormally warm seawater to these locations. So pretty strong evidence that warming sea temperatures and Vibrio infections are related. And that was highlighted in the Atlantic in 2014 when there was an unusually hot time for the Atlantic Ocean, the North Atlantic Ocean. Vibrio actually got as far north in 2014 as Sweden and Finland, where there were 90 documented cases, which is substantially higher than normal. They usually don't get any. So those warming sea waters came up. 2 years later, when there was an unusual cold period in the North Atlantic, Vibrio dropped. Vibrio infections dropped considerably. Kind of the poster child for warming seas and disease is the Baltic Sea, which has a lot of other issues as well. But sea surface temperatures in the Baltic Ocean are warming rapidly. Those warming patterns are correlating with more Vibrio infections in Northern Europe. A 2013 study in Nature Climate Change was one of the first to empirically correlate these Vibrio infections around the Baltic Sea to anthropogenic climate change causation. So there is finally a causal link, and that's for temperate regions. But basically in the Baltic Sea, for every 1 degree Celsius increase in maximum water temperature, you get an almost 2 times increase in the rate of Vibrio infections. So pretty dramatic link. Now, the one everyone worries about, of course, is cholera. Unless you get your skin infected with the other Vibrios, they give you about 5 days of bad intestinal problems, and that's it. But cholera obviously is a big disease worldwide. Cholera has a C phase, and this is a picture of cholera bacteria clinging to a copepod in the water. Globally, according to the Centers for Disease Control, cholera cases have been steadily increasing since about 2005 across the world. Currently, there are about 2.9 million cases of cholera and about 95,000 deaths each year around the world. And about 1 in 10 infected people get the really severe form of the cholera disease. There are various ways to get cholera, and the worst one is what kills you. The bacteria on these copepods live in brackish waters and coastal waters. You can, in fact, get cholera, like the other Vibrios, from eating raw or undercooked shellfish. That's actually been documented along the Gulf Coast of the United States. But much more commonly, you get it through contaminated drinking water, which is one reason why it's still not a big problem in the United States and Europe, but in a lot of the rest of the world. Outbreaks have been correlating with warming water temperature, nutrient concentrations, and plankton growth. So this was a study that was done trying to project where cholera might be amenable in future climate. This is where the dark red areas are where these copepod cholera bacteria attach. Currently thrive. There are a lot of outbreaks correlated with warming waters in the Indian Ocean, for example. But gotta aim this just right. All right. So in the future, depending on what models you want, what assumptions you're making about emissions and rising temperatures, cholera is going to have a lot more places to hang out in the ocean, potentially leading to more local outbreaks. And I have to say, the C phase of cholera seems to be associated with local outbreaks, not with pandemics, but still, cholera is cholera, and if you're one of the localities that gets it, not fun. So, besides the Vibrios, as we already heard about from Keith, warming water also promotes harmful algal blooms. Cyanobacteria in particular produces toxins that can cause serious and occasionally fatal liver, digestive, neurological, and skin diseases in humans. They grow better at higher temperatures. They actually like, a lot of the species like temperatures above 25 degrees Celsius, which is roughly 77 degrees Fahrenheit. And interestingly, with cyanobacteria blooms, the blooms themselves can heat up the water. So they cause this positive cycle where you get a bloom going, it warms up the water, they like that better, they keep blooming, and on and on and on. So some cyanobacteria have substantially expanded their ranges along the Atlantic coast of both the United States and Europe. So Florida may be getting them now, but probably lots more of the seacoasts along the Atlantic will be getting them soon. All right, so sea level rise. Now, there was a student presentation on malaria yesterday, which I didn't get to see. My last class was late afternoon on Tuesday, so I had to travel yesterday. But to the extent this repeats, I apologize for that repeat. But the biggest uncertainty in sea level rise is how fast land ice is going to melt. It's an increasingly important component of sea level rise, along with heat expansion and what land masses are doing. If you go back and read some of the earlier IPCC reports, when they talk about sea level rise projections, there's a footnote or an asterisk, depending on which report you're reading. If you look down, it says, ice melt is too unpredictable, so we're not factoring that into our sea level rise projections. And this gives you the range of uncertainty that ice meltings have. But again, like sea temperatures, every time the scientists check, the ice is melting faster and differently than they expected it to melt. So not behaving like the glaciologists thought ice should be behaving. I actually got to talk to one of the glaciologists who's been working on this for at least 40 years, and he said there used to be 5 pillars of ice that pin the West Antarctic ice sheet in place, and they're all gone. So it's not doing what we think it should do. So as we've already heard, sea level rise could be a lot of variation depending on what the ice decides it's going to do. Now, What we normally worry about when we worry about sea level rise is this. This is from San Francisco, and what 8 feet of sea level rise would mean for San Francisco. Basically, all the coastal infrastructure would be underwater, the port facilities would be in big trouble. But the actual height and inundation from storms. But if this wasn't brought up yesterday, this is something else to worry about with sea level rise. Sea level rise, most places on Earth increases saline and brackish habitats. Saline being defined as more than 30 parts per thousand salt, brackish 0.5 to 30 parts per thousand salt. About 5% of the mosquito species that transmit human disease are salinity tolerant or salinity loving, either one. And they are already found in many parts of the world. They obviously transmit malaria, dengue fever, and several other diseases. There have been some historic studies. The Asian tsunami of December 2004 increased the amount of saline and brackish habitat available, and as a result, the density of Anopheles sondacus increased, which is an important malaria vector in that region. So the islands of Andaman and Nicobar experienced increased rates of malaria. Same thing happened in Thailand after this inundation. So pretty good evidence that they are related, and that more saline and brackish habitat leads to more mosquito infections. All right, so here is malaria incidents around the world. What is interesting on this map is several countries thought they had gotten rid of malaria and now have it back. Peru being one of the big ones on the west coast of South America, about midway up one of the red countries. Had thought it had eradicated malaria, as malaria has been forcibly spreading in some places. It got it back and hasn't been able to get rid of it again. So malaria is, like I said, spreading, and most places on the planet, even if they don't have malaria, have mosquitoes that can carry it. Just a reminder, malaria was endemic to the United States, so it's not like we're possibly free from getting it back. All right. Okay, so models are forecasting a generally increased risk of malaria translation at higher latitudes, so moving out of the equatorial region and into the temperate region. Like I said, Peru's already gotten it back. The projection is that malaria will shift about 200 kilometers, roughly 90 miles, well, 110 miles, per 1 degree Celsius increase in global average temperature. And increasing temps also increase the rate at which mosquitoes bite, so you've got kind of a double whammy. There's more of them, they're biting harder. And there's also evidence that the freshwater mosquitoes, freshwater breeds of mosquitoes that carry malaria, can evolve fairly quickly to saline and brackish habitats. So Guyana, for example, got rid of malaria. It was transmitted in Guyana by freshwater mosquitoes. Got rid of that through various mosquito control programs. Those programs and some land use practices increased the brackish habitat in Guyana, and presto, they got malaria back, carried by saltwater mosquitoes. So you've got a lot of different ways it can come back. All right, but malaria is not the only mosquito-borne illness to worry about. Dengue fever, another disease originally associated with the equatorial region, has the capacity to spread with climate change, And it has shown up in some places, including in the United States, where it didn't used to be, most notably Florida. For a long time in the United States, if you were in the United States with dengue fever, you brought it with you from somewhere else. But there have been now autochthonous or native infections of dengue fever several times in Florida. 2009 was when there was a locally transmitted outbreak in Key West. There were at least 28 infections. 2010, there were 65 local infection cases in Florida. 2013, 29. But it's also happened in Hawaii. So Hawaii had native infections of dengue fever in 2001 and then again in 2011. And Texas fights a fairly continual battle to keep Mexican mosquitoes out of Texas. And so Texas gets both cases coming from Mexico itself, but also has had some locally generated infections of dengue fever. So we are starting to see these spreads. All right. So, and as we've already heard, sea level rise also makes storm surge much worse. And storm surge tends to do a number on sewage treatment plants. Katrina, one of the undertold stories of Hurricane Katrina in New Orleans is how narrowly New Orleans avoided an epidemic of waterborne diseases. They had sewage treatment failures all over where Hurricane Katrina hit. Sandy, same thing. I'm in New Jersey, so I'm not going to say a whole lot about Sandy because a lot of you experienced it firsthand. But same thing, had a lot of sewage treatment failures. Hurricane Harvey, in addition to flooding out oil facilities and toxic waste facilities, flooded out a number of sewage treatment plants and polluted a number of rivers. Hurricane Irma resulted in scores of discharges of raw sewage in Florida. And there were at least 9 million gallons of raw or only partially treated sewage dumped in the waterway. Because Florida is relatively flat, they need electricity to pump the water around, and when the electricity went out, the sewage treatment plants failed. Probably most devastatingly, Hurricane Maria, when it hit Puerto Rico, dumped a lot of raw sewage into people's drinking water. So these are very real threats. In my humble opinion, we've gotten really lucky in the United States to have avoided some of the diseases that could have happened. But of course, sewage brings with it all sorts of fun little microorganisms that can cause some really bad diseases, including hepatitis, which is becoming a bigger and bigger problem in the West. We've got some interesting social issues with the homeless that are causing hepatitis A outbreaks in the West. So something to be aware of if you're in the West in a really bad storm. All right, so last one. And like I said, this is the most science fiction-y of the lot. But what about the ice melting? Well, there's this thing that's been labeled the zombie diseases of climate change. That's not my label. That came from the Atlantic in 2017. That as the ice melts, they might reveal some diseases we really would have just rather stayed buried. And there's some real basis for this. Like I said, I know it sounds like science fiction, but in August of 2016, in Siberia, there was an otherwise inexplicable outbreak of anthrax. And it turned out that there had been enough melting to expose a reindeer carcass that had been infected with anthrax. And that seems to be the source of human infections of anthrax in Siberia. So one 12-year-old boy died from that, and at least 20 people were hospitalized, all right? Other bacteria can form spores, and spores can last for a long time in ice. That includes tetanus and botulism. So that's a concern. Scientists, for reasons passing understanding, have actually gone looking for viruses and bacteria in the ice. And so they have successfully recovered samples of the 1918 Spanish flu virus, which none of us really want to see again, in corpses that were buried in Alaska's tundra. So these viruses are down there. NASA in 2005 successfully revived bacteria that had been in a frozen pond in Alaska for 32,000 years. So the survival rate for some of these things is pretty long. Luckily, the thing they revive doesn't happen to infect humans, thankfully, but they could revive it. And 2 years after that, scientists managed to revive an 8 million-year-old bacterium. So these things survive in ice for a really long time. Like I said, why they went looking for the 1918 flu virus is beyond me, but they did. And so we gotta wonder what else is coming with all this melting ice, as science fiction as it sounds. All right, so that's the fun and games science-wise. Why do I actually think this is important to have this public health perspective for coastal adaptation? This is going to sound like a really obvious thing to say, but you'd be amazed how many communities don't do it. Public health officials need to be part of the coastal adaptation planning discussion. They are often left out. We tend to get focused on infrastructure and seawalls and beaches and forget, oh hey, yeah, maybe we need to be prepping our public health community and our hospitals for some of these other things that might be coming as well. I will say it's probably gotten better in the East and the Gulf as a result of all the major hurricanes that have hit. On the West Coast, still hasn't sunk in quite as thoroughly that some of these events come with public health consequences. Adaptation planning should include future disease risk, and that should spill into appropriate training for medical personnel so they can recognize new disease. Florida had an inkling it was going to see dengue, and it started training its medical personnel to recognize the symptoms of dengue when they saw it. That has helped. We need similar trainings for other things that might show up. Mosquito control programs may need to be started or expanding as part of sea level rise adaptation. And those can take a lot of forms these days. Not all of them involve toxic chemicals, but planning ahead, again, a good thing. Harmful algal blooms, I think Keith would agree with me on this one, provide a really good reason to get serious about nutrient pollution control, if you didn't have other reasons for getting serious about it. And then sewage exposure from storm surge suggests that we might need to be thinking about new building codes, or it was suggested earlier moving our sewage treatment plants further inland. My conclusion on all of these is if you're thinking about public health and the coast, it's got to be an all-hands-on-deck approach. There are things you can do with land use law, there are things you can do with building codes, there are things you can do in the public health sector itself, there are things you can do through the environmental laws to help address these problems, but first have to think about what they might be. And so thank you very much.